Hey guys, welcome. We're going to be going over the review for the Unit 2 test. Per usual, I'm going to be giving rather detailed explanations rather than the opposite. You can always put me on fast speak or, fast forward, or skip about to the problems that you want, if it's more than you need. I'd rather give you more than less. So, anyways, let's go ahead and just knock this out. Question number 1, state if the functions are inverses. So remember, there's two methods for this. There's method 1, which is a lot quicker than method 2. Method 1, we can just see if we plug one number into f of x, right, that's going to go to another number, it's going to calculate to another number. If that number it calculated to, when plugged into g of x, if it produces the original number that we plugged in. So, so we first need to pick a number that we need to plug into f, because that'll give us our output. We can then plug that into g. So what's a number I'm going to pick? I'm going to pick 1. 1's usually a good number, and when I look at this, 1 isn't going to give crazy calculations, so I'll just do 1, and that will go to 1 plus 1 to the 5th power. I just plugged that 1 in right there, and that's going to equal 2. Okay, so now I take my 2, and I'm going to go over to now g of x and plug in 2. So that'll give me the 5th root of 2 minus 1, and lo and behold, that gives the 5th root of 1, and that is equal to 1. And if you need an explanation on why that is, well, that's because 1 could multiply itself 5 times, and it would still equal 1. Right, so that would be 1, 2, 3, 4, 5 of them, which we could pull out, and it would be equal to 1. So notice, right, it circled back around, it came back to the 1, so these are yes inverses. Oof, that's a terrible R. Slightly better, but alright, so now method 2 is so method 1 uses only a single number. Method 2 is going to use a variable and hence prove all numbers. Now, can a single number cut the cheese? Absolutely. It can totally work. It's a great way of, running an actual test to see if it works. But method 2 is the actual formal way to do it, because it was, whoops, there's no E in there, method. It's the formal way to show it. So, meaning that there would be, that ensures all numbers work, because you're using a variable, and variables can represent all numbers. So we'll go ahead and we're going to take f of g of x. Right, so what does that mean? We are just plugging in g of x into f of x. That's all that means, right? Normally we put a number in there, this time we're putting g of x in there. So how are we going to write that? Well, I first write f of x, which is 1 plus, and then we're going to have that x squared, or sorry, x to the 5th. And now we're going to plug in g of x. So we're going to have the 5th root of x minus 1. Okay, notice, right, that is just g of x right there. So all I did, plug that right into there, just boop. So I go ahead, and as you notice, right, my 5th roots are going to undo each other. So I'll get 1 plus x minus 1. You can even cancel these out if it makes you feel good. And then you'll get equals 1 plus x minus 1. Well, we can always just think of it like this. And then it's pretty easy to see that the ones are going to cancel out, giving us just x, which means that whatever you put into this is going to be undone if you run it through both functions. One function undoes the other and gives you what you originally started with. Hence, they are inverses. Yes. Inverse. That's a much better R. Alright, so find the inverses. Now we actually have to find the inverses. We don't have to just validate it. Remember, how does the inverse work? Well, step 1, we need to switch y and x. Okay, switch y and x, and then we need to resolve it for y. So we'll go ahead, we'll take the inverse right now. So x equals minus 4 minus 3 times y divided by 4. And that's technically the inverse right there, but we do have to solve for y. We are not completely done yet. We do have to solve for y, so let's go ahead and do that. I'm going to multiply both sides by 4. So I'll get 4x equals -4. I know I didn't show my work there. I'm challenging you guys to start doing some of these things mentally. If you need to show that, go ahead and do so. Now remember, we always want to work outside in. We want to get rid of the -4 first because things will work out a lot nicer if we do. So we'll add 4. Oh, what am I doing? I'm now showing my work. We're going to stick to the spirit of challenging you guys. So I'm not going to write that. So I'm going to add 4 to both sides. So then I would get 4x plus 4 is equal to -3y. And then last but not least, that -3 is multiplying y, so we want to divide by a -3. Not just 3, but also the negative. We want to get rid of that. So we'll have -3, and that will be equal to y 4x plus 4 divided by -3. Now, granted, you guys do already have the answers. They're on the back of the sheet that you got. I'm going through this just in one shot, not checking my work. You know, when anyone does something like that, you're bound to make a mistake. So, of course, you know, if I make a mistake, A, I'm sorry for it, but B, that's a great chance for you to notice and earn some Z-Bucks. Just message me on Remind, and you can get those Z-Bucks. Alright, so let's go ahead. So we gotta do it again. Equation's a little bit more complicated this time, but if you have the concept, it's really not that hard. So we're going to do the same thing. Notice the concept's still the same. We want to switch x and y. And now we're going to go ahead and solve for y. So we subtract 2 from both sides. We get x minus 2 is equal to 2y to the 5th. We want to now go ahead and divide by 2. Remember, you always want to work backwards. Normally you calculate exponents first. So we're going to get rid of the exponent last, or get rid of the division first. We divide by 2 on both sides. We get x minus 2 divided by 2 is equal to y to the 5th. We take the 5th root on both sides. Remember, roots, powers, they're opposites. They undo each other. So we will get the 5th root of x minus 2 divided by 2, which is equal to y. Okay? And just like that, that should be your inverse. Okay, find the inverse of each function, then graph the function and its inverse. So, I think the easiest way to do this, kind of like I've been showing you guys, is just make a table of values. We're going to make a table for the regular. We'll call this one R. Whoop, there you go. And we'll make another table for the inverse. We'll call this one I for inverse. And it's the same deal as before, right? We can always use tables to map functions. We can always use a table to make a graph. So we're first going to make a table for the original function, and then we're going to flip that table and make a graph and use that to graph the inverse function. So let's go ahead and do that. Notice this isn't a particularly complex equation, and plugging in numbers like 0, 1, and 2, it's not going to give me any crazy fractions, so I'll go ahead and just pick the numbers 0, 1, and 2. So I calculate those. 0 times -8, 0 plus 5 is going to be 5. 1 times -8 plus 5 is going to be -3. And then 2 times -8 is -16 plus 5 is going to be -11. Okay, that last point is going off the graph, but that's okay. We'll get a general idea of where it's going. So first we're going to go over 0, up 5. So right there. Then we're going to go over 1 and down 3. And then over 2, down 11. That, you know, just judging by that trajectory, it'd probably be somewhere way at the bottom of the page. Alright, but either way, we can go ahead and connect those dots. Not a great looking line, but it gets the point across. Get it? Get it? It gets the point across. Okay. So now we'll go ahead and we will switch them to find the inverse. Remember, inverse always switching the x and y. So we'll do -11 and 2. We'll do -3 and 1 and 5, 0. Okay, so we go ahead, we graph these. It's going to be right there. And it's going to be right there, and that other one, it goes off the page, it's going to be somewhere like out there. And we can go ahead and connect these. just like that. When I look at this, something tells me that this is wrong. Now, how do I know this is wrong? Because when I look at this, I should see a perfect diagonal reflection, and I don't quite see that, right? I see them intersecting right there. Doesn't quite make sense. It should intersect along here. So I'm going to check my work, and lo and behold, when I go back here, it was -1, -3, +1. So, no Z-Bucks for that one. I did make that mistake on purpose. I want to see if you guys are paying attention. And also, it's really good to show how you can catch a mistake when you make one. This one's very easy. It's very visual. You should be able to see it when you draw it. So this is going to be over here, and we will then, with a better line, connect it like this. And now we go. Now, right, you can see how it's kind of perfectly reflecting, which is good. That means they are inverses. Okay, identify the transformations on the function compared to the original function. So 5 is just kind of as we're used to it. 6 has a little bit of a curveball to it, but it's not too complicated. So the original function is just f of x, and then we put all this stuff on it. Well, we see 1/2 on it, 1/2 that multiplies it. That is going to compress it by 1/2. Now, why is that going to compress it? That's going to compress it because it's being multiplied by a number that is less than 1, meaning the magnitude of it is less than 1. So anytime you multiply by numbers like that, things get smaller. Even if you did 1/2 times 6. 1/2 times 6 would produce 3. That number got smaller. So we're going to call this a compression, and how much it's going to compress by 1/2. Okay, now we can look at the inside. The inside we see a +3, but remember inside is opposite, so we're going to say left 3 on the inside. And then the second one we're going to see a -4. Remember outside is what we expect, but it's up and down, so this is going to be down 4. Okay, easy enough, right? Not too hard. You just got to know your transformation rules. Not only will knowing your rules help you answer this question, but it's also going to help you quickly eliminate wrong answers for future questions. We'll talk about that when we go to graphing. The original function, okay, so now our original function is not just f of x. It's something that already has some transformations built into it. So what does this mean? This just means that you're not starting from absolute 0. Where you start from is things already being multiplied by 3 and things already being shifted left by 2. So you just have to take that into account when you look at your new shifts. And what do I mean by that? Well, if we originally multiplied by a 3, well, now we're multiplying by a -6. So we have to think, well, how do we get from 3 to -6? Based on multiplication. And well, we multiplied it by a -2. Right? So that means that it is going to be stretched by 2. And it's also going to be vertically flipped. Now, why is that? Well, that's because we started from 3, and to get to -6, you have to multiply by a negative. So that means there is a vertical flip in there, right? It is being flipped one way or another. And then the 3 also went to a 6, so we had to multiply it by a 2. Multiplying by a 2 makes a stretch of 2. Okay, so you just kind of find that relative difference, and then that is your transformation. So now let's look at the inside. So you see -1 in there, and remember, we don't start from 0. This time we are starting from +2. So how do we go from +2 to -1? Well, we went back 3, right? To go from +2 to -1, you have to go -3. +2 minus 3 is equal to -1. So that's like we have a minus on the inside, or we go right 3. Okay, because remember, we originally started with +2. +2 shifts it back 2, and then we went to -1, which would shift it forward 1. That difference is 2 and 1, which is right 3. Now same for this one. Now notice we do start from 0 with this outside one. There's no transformation there. So we're just moving up 5. Okay, sketch the graph of each function. So this is what I was telling you about, right? Knowing these transformation rules are going to help you quickly find the correct graph. Now, this is going to be multiple choice test, so being able to quickly eliminate wrong answers is really going to help your score. It's really going to be beneficial. So we're going to first look at this, and we know our transformation rules. That's inside, that's outside. Plus 1 on the inside is going to go back 1. Plus 3 on the outside is going to go up 3. So that is our vertex. That's kind of like our starting point. And then we have a stretch of 2. Now, there's a couple ways to go about this. You can always make a table of values. You know, that is your tried and true method. No matter what the equation is, you make a table of values for it and you see what's going on with it. So I saw that plugging in -1 gave me +3. Well, I can plug in -2 and 0 to kind of see what's going on around that. If I did that, I guess I'll show the work down here. So for -2, we would have 2 cube root of 3 minus 2 plus 1 plus 3. Start to calculate that. I do inside the radical first. That's going to be the cube root of -1. So cube root of -1, that 2 is still on the outside. Plus 3. Cube root of -1, well, that's just -1. And that's going to be equal to, so -1 times 2 is going to be -2, plus 3 is going to be a +1. So that means that I plugged in -2 and I got out a +1. So I can go back 2 and I'll go down 1 to right there. So you can kind of already start to connect your dots and start to see how this is going to look. Now, the other thing is, you should also know what a cubic function is going to look like, generally speaking. Generally speaking, a cubic function, right, when you have your cubic, it's going to look something kind of like this. So you want to kind of keep an eye, like, think about that while you make this, and imagine how that pattern could kind of fit itself into there. So then we will also do the 0, so 2 cube root of 0 plus 1 plus 3, and this is going to be kind of similar. It's going to be 2 cube root of 1 plus 3, and that's going to be equal to 5. So when we plug in 0, we go up 5, and so that point will be right there. Now, this is, like I was saying before, right? If you know what this function originally looks like, when you know what this looks like, you can kind of imagine, you know where the points are already going to go, and you can kind of just change them based on the transformations. What do I mean by that? I mean a cubic function normally starts at its vertex, goes over 1, up 1, and it goes back 1, down 1. Those are usually the first 2 points you get around the vertex. But now notice, they would be there, except I was being multiplied by 2. So it's going to vertically stretch both of them by 2. So we go over 1 and up 2, back 1 and down 2. Now, you can only do that if you know what this function originally looks like. If you don't know what it originally looks like, you can't really do that. So, that's our graph. It's a rough looking image of it. You're going to want to look for something that looks like that, or choose none of the above if you don't see anything that resembles it. Alright, identify the domain and the range of each. So, I always think it's easiest to use a graph when doing this. It allows you to see it, so we're going to go ahead and make a graph. So, kind of like before, we're going to just quickly approximate where the vertex is. So, it's going back 3, 1, 2, 3, and down 1, 2. Right there. And then I'm also going to know that this function, right, my square root function, typically looks like this. It's kind of like half a parabola, but only the upper half. So this thing's going to kind of go like that. Now, do I know it's going to intercept right there? Not quite, but it's enough for me to get the domain and the range of it, right? I can find the intercepts, and that's good if I can, but I don't quite need to do that. I just need to find the domain and the range. So I'm going to look at this and say my domain, well, remember D comes before R, so domain is X and Y is X. So this can go from -3 to infinity. What are the end caps on this? Well, it actually can touch -3, but we can never touch infinity, so that goes there. Our range, remember range is bottom to top or down to up. We can go as low as -2, and we can actually equal that. And we can also go up to infinity. We see that it never stops, so we can go up to there. Okay, that's our domain and range. Alright, just pause it real quick to get some water. So, okay, let's keep on going. So, sketch the graph of each function. So again, you want to sketch this, and this can be really easy if you know your transformation rules and your parent functions. So we're going to look for our vertex, that's inside, that's outside. -2 inside is over 2, -5 outside is down 5, so right about there. And this is a square root function. I know that my square root function is generally going to go like this, when no alterations are made to it. So I'm going to sketch this just like that. And another thing to know about square root function, its first point is typically over 1, up 1. Right 1, up 1, that's usually the point right there. And you can plug that in if you want to verify it. But that's what it's going to usually look like. Okay, graph each equation. So same deal, I'm going to look at this. Transformation rules are going to make this quite simple. So -3 is going to be right 3, and then +1 is going to be up 1, and my absolute value function typically looks like this, but it's now been shifted over to here, so I'm just going to go like this. Okay, and another thing to know about this, usually the first 2 points, forwards and backwards, are up 1. So it's usually right 1, up 1, and left 1, up 1 for this function. And when would those change? If we had a stretch of 2, we would then expect them to go twice as high. Alright, same deal. We have to graph this. So we see this is going to be right 1, this is going to be up 3. So we're going to go right 1, we're going to go up 3 to right there. Now, again, so here's where it can change a little bit. So typically our function looks like that, our absolute value function. I see a -3 that's multiplying this, so that tells me a couple of things. First, right, so number 1, this thing is going to be going downwards, kind of like this. And number 2, this also tells me that my function is going to be then stretched by 3. So it's going to be stretched vertically by 3, so I'm going to expect it to be more narrow. Now, how does this map onto the coordinate plane? And, well, side note, so, right, as soon, like, if you can kind of just even imagine that, even if you don't have actual numbers to it, if you just imagine it flipped upside down and skinnier, you can probably find your right answer just from that. But let's go ahead and be a little bit more exact. What would the 2 side points be? Well, accounting for the multiplication of -3, they're going to go downwards, like I said, and they're going to be stretched by 3. So instead of going over 1 and down 1, we're going to go over 1, and 1 times 3, well, that is 3. So we go over 1 and down 3. Likewise, we're going to go back 1, and then instead of down 1, we're going to go down 3. Right, because 1 times 3 is 3, so it gets multiplied or stretched like that. And that's why those multipliers stretch your function. They're making it more elongated. Now, say that's kind of, that conceptually, you know, it rocks your world, you can always go back to your table. Now, is this going to take more time? Absolutely. But is it going to be, you know, if this is the method you know, do it like this. You know, this is about you getting the right answer, and accuracy is always number 1. Even, you know, even on a test, you want to get every single question that you do right. You know, if you're skipping questions because you think they take too long, that's bad practice. You always want to have some methods to do a question. So, You can plug in points around here to see what it's going to look like. I'll plug in 0, and then that would calculate to -3, absolute value of 0 minus 1 plus 3. This is going to turn out to be 0. 0 minus 1 is -1. Absolute value of -1 is 1, and then 1 times -3 plus 3 goes to 0. Alright, we'll do 2, or, oops, sorry, -3, and then the 2 goes inside. -1 absolute value plus 3. Alright, so actually same deal with this. This one is also going to go to 0. You can do those calculations. 2 minus 1 is +1. Absolute value +1 is 1 times -3 is -3 plus 3 is 0. So both of those go to 0, and that perfectly lines up with what we predicted. Okay, so this is always method number 2. It's a little bit longer, but this is a more developed method. It takes a very strong understanding of what they originally look like and then how transformations are going to affect a function. Okay, sketch a graph of each function. So you gotta make a graph of these. You have two different formats. You have standard form, right? This is standard, and this is vertex. Okay, vertex might be a little bit easier, so I guess we'll go ahead and start with this one. So we see the vertex is going to be shifted over 1 and up 4 to right there. And now, again, it's really good to know how your equations typically look, because, then you don't have to do all these calculations. So parabolas typically look like this, and their points right around the vertex are usually right 1, up 1, and back 1, up 1. So we look at this, and it has a multiplier of a negative, so it's going to still be those same points, but flipped upside down. So instead of going right 1, up 1, we're going to go right 1 and down 1. And likewise, we're also going to go left 1, and instead of up 1, we're going to go down 1. Just like that. And we can start to imagine this. Just like that. Okay. Now, I did intentionally make it cross right there. The reason why I did that is because I also know that the second point from the vertex is usually over 2, up 4. That's due to the square of it. It usually has that parabolic shape. So instead of going up, it's going down now, so it would go over 2, down 4, over 2, down 4. Alright, so that's probably the easiest way to do that. You can use your table if you want to. You can use 1 and 4. If you're understanding if you can't quite remember those features about a quadratic, you can always start plugging in numbers and see what happens. Okay, we plug those in, we calculate them, and we would get 3, right? 0 minus 1 is -1, squared is +1, -1 plus 4 is going to be +3, 2 minus 1 is going to be +1, squared is just 1, -1 plus 4 is still going to be 3. Okay, so, the math does check out. That's what our graph is going to look like. Alright, so standard form, this one's a little bit trickier. Remember, right, standard form we can't quite work with. We have to factor it. So we can't exactly extrapolate a lot of information from this until we factor it. Well, what can I tell from it? I can tell that my y-intercept is going to be -3. Why do I know that? Because y-intercept is when x is equal to 0. And if x was equal to 0, it would kill that term, and -3 would be the only one left. So I can immediately know my graph is going to have that point right there. Where's the rest of it? Well, let's go ahead and graph it. So, to start graphing this, I guess let's find the x-intercepts. So to find the x-intercepts, I'm going to need to factor this. So remember, factoring a trinomial, we do a times c, adding to b. So a times c is going to be -3, b is going to be 2, and what are those numbers? It multiplied -3, but add to 2, that'll be 3 and -1. So this will be equal to, we can take our shortcut, x plus 3, and x minus 1. Really crammed it in there. God, that's messy. Okay? So that's what our equation looks like once we factor it. Here, I'm going to write this down here. That'll be equal to x plus 3 and x minus 1. Okay? Remember x-intercepts, x is equal to, or y is equal to 0, so we say 0 is equal to x plus 3 and x minus 1. So x, right, by the zero product rule, is going to be equal to negative 3, and x is going to be equal to 1, right, because one of those would have to go to 0 to multiply to 0, so we would choose the opposites of what's inside there. Alright, so those are our two x-intercepts, so we'll put one at negative 3, and we'll put one at positive 1. And I can already tell my axis of symmetry is going to be right in the middle of those two coordinates, right there. And I can also, right now, I can go ahead and know that that's my axis of symmetry. I can put a point right there because these points would be reflected across the axis of symmetry. So I can start to graph these, and maybe you can already kind of piece together the parabola. Whoop. Right, you can start to piece it together, and you can kind of imagine where the vertex is going to be. It's going to be somewhere around here. But let's go ahead and mathematically calculate it. I'm going to use well, I guess at this point I can see that that for my vertex, that for my vertex, x is going to be equal to negative 1. So I'm going to go ahead and just plug in negative 1 to find out my vertex. So y will be equal to negative 1 plus 3 and negative 1 minus 1. Alright, so that will be positive 2 times negative 2, which is equal to negative 4. And, you know, lo and behold, our vertex is right there. Kind of made sense, and this can also make sense with what I just previously talked about, right? Parabolas, they usually go, the points around the vertex usually go over 1, up 1. So we can look at this one, we see it goes over 1, up 1, and back 1, up 1. So that's good, right? Everything's kind of checking out, so we know that's the graph. Alright, I identify the vertex of each. So here's where I'm going to use the other equation that we haven't practiced too much, but that equation that we haven't practiced too much, we're going to use that here, and we're going to see why it can be helpful. Now, do you have to use that? Not necessarily, but I think it's really good to be able to use that. So, what would the vertex of this one be? Well, I'm going to use the x is equal to negative b divided by 2a, and that finds me the x value of the vertex. Right? That's just an equation that we have. There is good reason for it. We haven't discussed it, but this is always going to find the x value of a vertex when something's in standard form. So we can go ahead and plug and chug, and we get negative 40 divided by 2 times a, which is 2. So that's going to be equal to negative 10. Okay, so the x value for our vertex is negative 10. We can now go ahead and plug this in and calculate what our y value will be. So we have y is equal to 2 times negative 10 squared plus 40 times negative 10 plus 198. Alright, calculating that, that's going to be positive 200. Whoops, not 2,000. This is going to be minus 400, and this is plus 198. So that's pretty nice. That works out kind of well, right? 198 is just 2 away from being 200, so that'd be like 398 minus 400, which would be equal to negative 2. Okay, so our vertex is going to be the coordinate negative 10, negative 2. Okay, that equation is going to save you some time. Instead of doing your factoring business, finding your x-intercepts, finding the average of those, this just takes you directly to the x value of the vertex. So it's a good equation to know. I would definitely memorize it, and you can use it. Now, could you have done it the other way? Yeah, you could have factored those. You could have found the x-intercepts, could have found the average, but this is going to be a lot quicker. So it takes you directly to the x value of the vertex. Alright, identify the axis of symmetry. So this one is, I kind of think of axis of symmetry problems like a really easy vertex problem. And why do I say that? It's because the axis of symmetry is just the x value of the vertex. So all you need to find is the x value of the vertex, and you have your axis of symmetry. So notice, right, when we go to find the x value of our vertex, well, that's actually, we have an equation for that. It's x equals negative b over 2a. Now, could you factor that? Probably. Could you do that whole method? Yeah, probably, and it might work. Depends on if it factors. But this is going to be pretty quick, and it's going to just take you right to the value of x for the vertex. And remember, like I said, that x value of the vertex is the axis of symmetry. And if that kind of confuses you, just take a step back and look at a parabola, look at the axis of symmetry, and see how the vertex and the axis of symmetry relate to each other. So we'll go ahead, we'll plug in negative 30 divided by 2, and a is equal to 15. So that will be equal to negative 1, because 2 times 15 is 30. Divide them by themselves, x will be negative 1. So our axis of symmetry, right, like I said before, it's like a really easy vertex problem, is x equals negative 1, just the x value of that vertex. Alright, identify the vertex of each. These are even easier. This is in vertex form. Vertex form is specifically made to see what the vertex is. So we can look at this and we know that our vertex is going to be negative 5, comma 5, right? Back 5 because it's opposite inside, up 5 because it's the same outside. So that's our vertex. Identify the axis of symmetry. Well, remember, that's like a really easy vertex problem. You just need to find the x value of the vertex. So we can look at this, we see the x value is going to be opposite inside, which is plus 7. So our axis of symmetry will be equal to positive 7. Okay, so our AOS is right there. Just positive 7, right? It's like a really easy vertex problem. Alright, identify the x-intercepts of each. So x-intercepts, remember, y is always going to be equal to 0. So we'll need to set these equal to 0, and then we can go ahead and solve them. Okay, now this one is in vertex form, and you can kind of follow your intuition on this one and just start solving for x, because as soon as you get rid of all those operations around it, you'll have x isolated, you'll know what x is equal to. So we'll add 9 on both sides, and we will get 9 is equal to x minus 3 squared. We now need to get rid of the square, so we will go ahead and take the square root on both sides. But now we need to remember that we need to write plus and minus in front of that square root, because anytime we take a square root, there could have been a positive or a negative underneath that square that we didn't account for. So square root of 9 is just 3, plus or minus. Oof. Let's rewrite this. Alright, so this will be plus or minus 3, which will be equal to now just x minus 3. We're going to add 3 to both sides, so I'm just going to scoot my plus or minus 3 over, and then add 3 to it. Okay. Remember, when I write plus or minus, that's just a shorthand way of saying both the positive and negative 3. So there's two values that are stored in there, positive and negative 3. So when we go to calculate this, we're going to have to do two calculations. We're going to have positive 3 minus, plus 3 will be equal to x. And we're also going to have minus 3 plus 3 is equal to x. So we're going to see that x will be equal to 0, and x will also be equal to 6. So those are our x-intercepts right there. Note, this is the same thing, they just it's two different ways of looking at it. You can write it however you want. It could be in a test, either written like this or written like this. You need to know that those are the same. Okay, we'll go over here and we need to do the same with this. So we have to identify the x-intercepts. So now over here we have standard form, so we can't just quite go about solving this like you might typically do. The reason being because, if you try separating the x or isolating the x, you have two instances of x. And that's an issue because how can you separate your x or isolate it if you have two x's, right? It's never going to be isolated. You can't combine these, and no matter what you do, this will always, there's always going to be two x's, so you can never isolate it. And that's why we want to resort to factoring, right? So when we see a trinomial like this, we can go ahead and try to factor it. So the first thing I notice is that I have a greatest common factor of 3, because all those numbers can be divided by 3. That's going to give me x squared minus 4x and plus 8. Is that right? I feel like that's not right. That's not right. Oh, wait a second. Can I not factor this? Hold on one sec, guys. Alright, that's my bad. Looking at this problem, you wouldn't be able to factor out a greatest common factor of 3, and so you would actually need the advanced method of factoring in order to solve this. So don't quite worry about this one. What you do want to practice is finding the x-intercepts of something you can factor. So I guess for right now, don't worry about this one. If you want to see something you could practice, look at y equals, and we'll say 3x squared plus 18x plus 15. Okay, this one you can factor, so we can go ahead and pull out a 3, and we would get x squared plus 6x plus 5. Now we can go ahead and do our a times c, adding to b. That would be that would be 5. Adding to 6, and what would those numbers be? That would be 1 times 5. 1 times 5 would multiply to 5, and 1 plus 5 would add to 6. So we can then write this as 3 multiplied by x plus 1 multiplied by x plus 5. Oh, there we go. Okay, so it would look like that, and remember y was set equal to 0, so now using that 0 product rule, we can say that x is going to be equal to negative 1, and x is going to be equal to negative 5. Okay, those would be our x-intercepts. Y was set equal to 0, we factored it, and we then found our x-intercepts. Now we have to find the y-intercept, so we've done this previously, but it's just asking for it explicitly. Remember that when we're looking for the y-intercept, we're going to be setting x equal to 0. So x is going to be set equal to 0, and we're going to go ahead and just calculate them. So we have y is equal to 0 plus 3 squared minus 3. How do I know I can calculate that? Because I have y that is isolated, and I have numbers over here which I can calculate. So we will have 3 squared minus 3, which is equal to 9 minus 3, which is equal to 6. Likewise, so x is going to be set equal to 0, so y will equal, and you'll see that this is pretty easy. We're going to plug in 0, and there's a lot of terms that are going to die here. They're just going to go away. So 0 squared makes 0 times negative 3 is 0, so that just goes away. Negative 60 times 0, well, that goes away too, and we're left with y is equal to negative 301. Pretty simple, and that agrees with what we said before. That is our y-intercept right there. Whew, okay, final stretch. Alright, so factor each completely. So we are going to do our a times c method right there. So a times c will be equal to 15. And b will be equal to negative 8. We want to find those numbers that multiply to 15 but add to negative 8. And I can think, well, 5 and 3 would multiply to positive 15, but they wouldn't quite add to negative 8. They would add to positive 8. How can I make that happen? Well, I could say negative 3 and negative 5. And so then I found my perfect numbers. I can take my shortcut because a is equal to 1, and I'm just going to write n minus 5 and n minus 3. And those are my factors. Okay. Same deal over here. We need to factor this, but notice, right, we have b cubed, we have a b squared, and we have a b. That means, we have some extra b's in there, but that's okay because they can all ante one up or kind of contribute a b to be multiplied on the outside. So now we could write b squared, and we can check it as we go. B times b squared is b cubed minus 15b, right? B times negative 15b goes back to b squared, and then plus 50. Alright, so now we have this. We can see that a times c is going to be equal to 50, and b is going to be equal to negative 15. What are those two numbers that add to negative 15 but multiply to 50? Well, I could, might take a couple guesses before I finally get it, but once you get there, those numbers are going to be negative 5 and negative 10. If you're unsure of, if you didn't quite see that and you weren't sure how to get those, just plug in anything that could multiply to there. You could even do 25 times 2. You want to list all the factors of 50 if you can't, if you're not sure where to go. If you're kind of stuck, you can't see it, list all those factors. Alright, and so then these are our two magic numbers. So a is equal to 1, so that's good. So we can just write, whoops, sorry, these are b's, not x's. B minus 5 and b minus 10. Just like that, and that's our final answer. Right there. Whew, last page. Okay, solve each equation by factoring. So remember, this is pretty easy because if we get one of them to go to 0, everything will multiply to 0. So this will break apart into two equations. N minus 2 is equal to 0, and n minus 4 is equal to 0. We solve this and we'll get n is equal to 4. We solve the other one and we'll get n is equal to 2. Okay? Maybe you didn't need to show all those steps, but that's the formal math that's going on behind it. We know either one can equal 0 and they'll multiply to 0. Therefore, we make those two equations. Okay, now over here, this formal method might actually help you a little bit more because you're going to have a couple operations with one of these. Or a couple things to do in order to solve it. So, but notice, we still set it up just the same. Both of them, if we get it equal to 0, give me one sec. Alright, cool. Thought someone was in my house. Really weird. Alright, so So back to this, right? We said both equal to 0. We know that if one of them equals 0, the whole thing will go to 0. So we set each one equal to 0. And then we go ahead and solve. So this one's pretty simple. This one's just going to be x equals -2. Right? We subtract 2 from both sides. That's how we got there. This one might take a few more steps. First, we would have to add 1 to both sides. So we would get 4x is equal to 1. Then we would have to divide by 4. And then we finally see that x is equal to 1/4. Okay, so a couple more steps, not terribly hard, but it would probably be helpful to write that out. Alright, and the very last question, we need to solve this by factoring. So the earlier ones are pre-factored, this one is not pre-factored, so we're going to have to do our a times c stuff. And notice this is just the same as finding your x-intercepts, so really, it's not a new concept. You're kind of just being asked the same concept over and over again for different questions. So a times c is equal to 5. That's equal to -5. And b is going to be equal to -4. So we're looking for what could multiply to -5, but add to -4. And we stop and think about it. Well, what about, there's only a couple factors of 5, particularly -5, so what if we did -1 times 5? Well, that would work for -1 times 5, because that would equal -5, but -1 plus 5, that'd equal -4. So what could we do? Well, we could change the number that the negative is on, because it still multiplies to -5, but now it will add to -4. So we can now, if we find our magic numbers, we'll take our shortcut, and this will be equal to x plus 1 multiplied by x minus 5. Now we're back to step 1, kind of like with here, and we will set each of them equal to 0. 0 is equal to x plus 1, and we will see that this is equal to -1 with a little bit of algebra. And then for this one, 0 is equal to x minus 5. So kind of the same deal, except a little bit of algebra shows that this one is equal to +5. And those are our two x-intercepts. And that concludes the review.